So in the last video, we talked about a brute force algorithm that can be used to find initiation interval constraints by looking at possible overlap in reads and writes between any two iterations of a loop. So this time we're going to look at what's wrong with that brute force algorithm. So two things should come to mind immediately. One is that actually checking every pair of iterations might be impossible, right? So what if the number of loop iterations depends on the input data? Then we can't check all iterations because we don't know how many there might be. The other problem is that even if we do know how many iterations there are going to be, it might just be impractical to compare every pair of iterations, right? What if the loop's going to run 1,000,000 times? It's just not practical to compare every pair of 1,000,000 iterations and see if they overlap. But there's actually a third problem, and this third problem, which we're going to talk about, will give us a window into how we can create a more efficient algorithm that does the same thing. So let's just try a different dumb example. We're going to use the exact same program, but instead of the loop going from 2 to 5, it's going to go from 2 to 10. So now our dumb algorithm is going to look like this. For k equals 1 to 8, and for j from k to 8, if k plus 2 equals j, we're going to add this constraint. And just for convenience, let's reorganize this a little bit. Let's just abbreviate the instruction as instruction, INSTR. So we're going to add a constraint of this form, and we're also just going to simplify the arithmetic here. So I'm going to move this term over to the right side. So instead of plus ii times k minus j on the left side, we're going to get plus ii times j minus k on the right-hand side. So just a little algebraic rearrangement and simplification. Now, if you run this program just mentally, what you'll see is that there's a couple of constraints, right? We're going to add constraints when k is 1 and j is 3. We're going to add it when k is 2 and j is 4, when k is 3 and j is 5, when k is 4 and j is 6, when k is 5 and j is 7, when k is 6 and j is 8, and then that'll be it. Okay, well, let's look at the constraints we add. So here's the constraints we're going to get, and when we simplify it, they're actually all the same, right? It's at the end of the instruction is going to be less than or equal to the start of the instruction plus 2 times the initiation interval. Okay, so actually, we could have picked any one of these instructions, forget about the rest of the iterations of the loop, and any one of them would capture all of the others. So will this always be the case? Well, it won't always be that all the constraints are the same. So next time we're going to look at a slightly different example, and we're going to see that even if we don't get this case where all the constraints are exactly the same, we will find that every constraint generated by the dumb algorithm will have the property that for the entire set of constraints, there'll be exactly one constraint in the set that implies all of the others. And just to give you a teaser of why, the reason is if you look at the form of this constraint, it only depends on the difference between j and k, right? Everything else is invariant of the number of loop iterations. The initiation interval is our variable we're targeting. The start and end of an instruction are properties of the basic block schedule. So actually, the form of the constraint only depends on the distance between the loop iterations that share a read or a write, or that have a read-write dependence, and not on the absolute number. And so next time we'll just look at a slightly more sophisticated example, and from there we'll talk about a more general way to find constraints on the initiation interval that's both simpler and more efficient for a large class of programs.